for our next speaker is Abdulkadir Canatar. He's a PhD student at Harvard, and he's going to talk about the statistical mechanics of generalization in kernel regression.
Hello, everyone. I'm Abdul from Harvard, and I'm going to present our work with Blake Bordelon and my advisor, Cengiz Pehlivan, on statistical mechanics of generalization in kernel regression. So first, I want to start with the background. The main goal is in machine learning is to train a model to generalize to unseen data from the training data available. And in modern machine learning, mostly what we see is that, the models are over-parameterized, so there is orders of magnitude more parameterized than number of data, such as deep neural networks. So why this is interesting? It's because of the usual machine learning concept, where here, for instance, I want to fit this blue dots here, and then the optimal model is a parameter with degree 4, but the parameter model with degree 15 actually overfits. So this is not generalizing well, and then this can be summarized in this plot here. In this case here, what you see is that test risk increases as you fit the data more and more, and at the end you interpolate all data, but what you find is a bad generalization. However, in modern machine learning, what happens is that after this interpolation threshold, if you increase the model complexity more and more, you start generalizing well again. And this is called double descent phenomena. This phenomena somehow implies that fitting all training data plus generalization somehow implies that there's an inductive bias happening in the over-parameterized model. And this model has been studied very rigorously in random futures model community, where what they find is that if the number of parameters is equal to number of data, you have this interpolation threshold, you diverge, and then after some time, you generalize it again. But the main reason here is why we see double descent phenomena as a summary is that is because of it's due to the variance in the parameters, the randomness in the futures you have in your model. In this talk, we will fix the futures. So there's going to be there's going to be fixed futures. So we won't be able to see this double descent phenomena, but we will see more interesting things. So we will work on this edge of the spectrum. Okay, so today what we will do, I'm gonna try to understand how generalization improves or changes with number of samples in kernel regression. Specifically, I wanna ask what the inductive bias is and how does it depend on kernel and input distribution and label noise. Why do we study kernel regression? Because it is analytically tractable. It's also relevant to modern machine learning. What we mean is that it can fit all training data and it can also generalize. There's also relevance to deep neural network via the celebrated neural tangent kernel. So we might even find applications to neural networks. And eventually what we will get is a predictive theory of generalization, which is applicable to any kernel and data distribution. And this includes, of course, neural tangent kernels. Okay, so first I want to introduce what kernel regression quickly. We fix a data set, data distribution, and I assume there's a target function such that I pick my labels noisily from this target function. And I will create a training set of size P, and I will also fix a hypothesis class, which is called reproducing kernel Hilbert space with a kernel K. Our aim is to minimize the mean square loss function with a Hilbert norm regularization. But notice that this function is going to depend whenever I choose a different data set. So what I want to do eventually is that when I calculate generalization error, which is basically the mean square loss between the target function and the function I learned, I want to average this over all data set distributions. Okay, so but this is a hard calculation to do because I don't know how to get an analytic expression for f star d given any random data set. So instead, what we do is that I will just state that this problem is completely equivalent to calculating this function integral. Why? Well, basically, this exponential here will concentrate as beta goes to infinity to the true value, like the minimizer of this problem. And then here I also put my generalization error so that when I take the derivative, I will be able to calculate this generalization error. So it's just convenient to calculate Gaussian integrals rather than doing more, I don't know, abstract stuff. Okay, fine. But in order to calculate this function integral, first I need to decompose my functions into some orthogonal basis. This is how we do. I take my data distribution, I take my kernel, and I try to solve this eigenvalue problem. Here, these 5 rows are going to be my orthogonal functions. And then later I define my futures via square root of the eigenvalues times this orthogonal functions. And if you follow Mercer's theorem, then the kernel can be expressed in this form. And therefore, any function in this Hilbert space can be expanded in terms of this future orthogonal future functions. Okay, so then what I do, I write my student function where I call my W row as my weights, and then I write my target function where I call my W row bar as my target weights. And basically what students is trying to do is to match this W row bars. So eventually it simplifies, it just becomes a nice Gaussian integral. And then by following this procedure, I will be able to calculate generalization error. However, I need to average over all training data sets, basically average over these quantities. But average of a logarithm is usually hard. So what we do is that we will resort to replica trick, where we will actually duplicate this statistical model n times and take the average of that over the data set, and then take the limit n goes to 0 to obtain this guy. And on the way, we need to impose something called replica symmetric alpha. So without going into too much details, this is what my result is. First of all, what we find is that the generalization error decomposes into mode errors for each separate mode. And the mode errors is given by this complicated equation, which depends on my kernel eigenvalues, teacher weights, and the noise variance. And plus there's this complicated self-consistent equation we need to solve in order to obtain what generalization error is. I want to stress that this result is only exact as p goes to infinity. So if you think naively that generalization error in this limit is going to be always 0, unless you have some other parameter in your model which diverges or which goes to infinity as p goes, and then we will come back to this point. However, now I want to show naively, I just want to take this equation and then apply this to real data sets, right? And then I'm just gonna see if it works in finite p2. Okay, so okay, so what I obtain is the following. Basically, my eigenvalue problem, if I pick my data distribution as the empirical distribution, reduces to a KPCA problem. And then once I solve the KPCA problem, obtain this eigenfunction, eigenvectors, and eigenvalues, I can find the target function by projecting my eigenvectors on the data labels, and then plug everything into this formula and guess if my generalization error formula holds. So here's an example. This is a Gaussian RBF kernel, and I have 2 different tasks. One task is the classification of zeros and ones from MNIST, and the other task is the classification of 8s and 9s from MNIST. As you can see, this is a much more easier problem than this one. And then if I naively do the regression, you see the dashed lines here as my theory, and then the blue dots are the experiment. And theory and experiment really fits perfectly. So now I want to analyze some stuff about this. First, I want to check how the eigenvalues look like for these 2 different tasks. They look almost similar. So this definitely doesn't make a difference because, as you can see, 8 and 9 task converges slower than the 0 and 1 task. So what happens actually if you calculate the cumulative power, which is defined by the total power, placed in the several eigenvalues until kth eigenvalues. And what we see is that the 0-1 task places most of its power to the first few modes, while the 8-9 task places most of its it is more uniformly distributed in terms of power. So there's more power in higher modes. And what we observe is that generalization error falls slower when power is distributed more uniformly over all complicated features too. So there's another example here. So in this case, I compare MNIST and CIFAR10, plus I also add some label noise for the Gaussian RBF kernel. So what I find here is that MNIST and CIFAR, so first of all, MNIST converges much faster, achieves the zero training test error much faster. And when I have label noise, I also see this non-monotonicity in my generalization error. Again, I compare different eigenvalues for these two kernels. They still look the same, but what makes the difference is really this cumulative power, where MNIST places most of its power to the first maybe 1,000 modes, while CIFAR10 is most uniformly placed here. So we find that the faster learning happens when most of the power is on the first few eigenfunctions, eigenvectors. And this is what we call task model alignment, which simply tells you which kernels are best for a given data set. What I mean that which kernel actually lets you place more power in the first several eigenfunctions. The second one is that this I'm not going to show rigorously right now, but this also implies that first several eigenvalues are learned first. This is what I call spectral bias. Why? Well, because the learning machine can learn up to here very fast. Both of them are going to learn up to here, but it's going to, for instance, CIFAR case, it's going to fall slower because it has more power in the higher modes. So you need to wait a bit more. You need to give more data to learn those modes. Finally, there is a label noise, which causes non-monotonicity in EG. At the beginning, we said there's not going to be a model-wise double descent, but this is called sample-wise double descent. As I give more and more data, sometimes it hurts my generalization performance. And we will explain this more analytically later. Okay, so now let's come to that. So if I want to obtain a non-trivial result here, I need to first of all observe that there is this combination P times zeta rho, my eigenvalues. So if I somehow find my eigenvalues scaling inversely proportional to P, then I can obtain a finite generalization, non-trivial generalization error, and I would be done. So this can be achieved in dot product kernels, which is a really generic class of kernels, where the kernel only depends on the inner product of two inputs, such as Gaussian, RBF, or NTK. And I will further assume that I have a synthetic data set. I pick my data from a uniform distribution of D sphere. And eigenfunctions in this case are going to be spherical harmonics. We know that these eigenvalues of the kernel, when they have rotational invariance, they have degeneracy and DL, which goes like D to the L. And we also find kernel eigenvalues are going to scale inversely proportional to this. Here's an example. Here's the NTK spectrum for several layers. And then what you see is that the combination of eigenvalue times the degeneracy stays constant as I increase the dimension. So this basically says that eta L times NDL is order 1 with respect to dimension. Then what I do, as usual, I will just take my number of samples and the number of input dimension to infinity while keeping this specific ratio order 1, where this degeneracy is the degeneracy of mod T, and it can be integer. It can be any integer. So let's see what happens. I find out in this limit that there are several learning episodes. If I'm in learning episode T, and if I'm looking at the mode error of mod L, which is smaller than T, I find that the generalization error goes to 0 for that mode. For L larger than T, I find that it doesn't change much as I feed more and more samples. And what I find is that when L equals to T, it is just an order 1 function, which I will show soon. Here is an example of this. This is again, this is like for D equals 20 input dimensional sphere. What I find is that the K equals 1 modes learned first when P is equal to the degeneracy at that point, at that mode. And then, you know, hierarchically, they start falling as I feed more and more samples. And then when they hit the degeneracy at that mode, they will start going down. And actually, you can analytically even show this from our theory, where if lambda rho is bigger than lambda rho prime, the percent change in the generalization error is going to be larger than the percent change in the generalization for the later mode. This is called spectral bias. And now let's study the generalization error in this limit. This is basically what I obtain. Here, sigma tilde square is what I call effective noise. And lambda tilde L is what I call effective regularization, which just appears here. And there is also two different terms. One is noiseless term here. If you are a random future models or random matrix series, this is the bias. And there's a noise term. This is the variance. And if I look at their graph, these are dimensionless quantities, so I can just look at them with respect to alpha. And what I see is that for larger effective regularization, the noiseless term decays slower. And for larger effective regularization, noise term, first of all, noise term as 0 effective regularization diverges at alpha equals to 1. And for larger effective regularization, then these peaks are smoothened out. So there's more regularization. So this is kind of like a bias variance trade-off. If you have noise, maybe you don't want so much peak, so you need to increase your effective regularization, but then you're gonna fall slower, achieve your generalization slower. So let's make an example here. Imagine that my eigenvalues are obeying a power law. In this case, you can explicitly calculate effective regularization, which looks like L over S minus 1. And here you can explicitly see that higher modes and slowly decaying spectra, which basically means smaller S, imposes more regularization, which is perfect because we expect this from a model with inductive bias where higher modes are regularized more. So actually you keep your function smoother. This is what we call this is how we characterize or formalize our inductive bias in kernel regression through our effective regularization, and it only depends on the eigenvalues of the kernel. An interesting thing, for instance, for neural networks, lambda is 0. There is no, explicit regularization, but there will be always this implicit regularization, effective regularization, just because of the decay of the spectrum. So this kind of, so this is the implicit bias. And now next I'm gonna ask, when does double descent occur? When I see a non-monotonicity in my model, basically what I do is that I take the derivative of my generalization error with respect to alpha, and I find a function which tells me for which regularizations and for which noise I will see double descent. Here in this graph, in the dark blue region, you see there for the combinations of lambda tilde L and sigma L. In the blue region, it's just monotonic. Generalization error decreases monotonically. Even there's a label noise. So basically, higher regularization will lead you go more monotonically in generalization error. The dark green region is generalization error where it has only one critical point for this equation. And then light green is what we call double descent, where there is one minimum in generalization error and one maximum. It basically goes down, up, and goes down again. So this is our double descent phase diagram where this red line basically tells me, given what effective regularization and given what noise, I will have double descent. Second, I will ask if there's an optimal effective regularization, because we already said that there's a bias variance trade-off with respect to effective regularization. And yes, if we differentiate, next we test our model on this synthetic data case, where I again choose Gaussian RBF with this model. And then first I plot my generalization error when there is no noise. There is again a really good fit with theory and experiment. Then next I pick this line here, and then I identify some points and then do kernel regression. What I find is that the yellow line is always lower if I choose my noise and my lambda effective regularization to be same. It is always lower in this region than the other ones if I pick my lambda smaller or bigger. So this basically says that, and these are my double descents. When lambda is really small, you really see this peaks here, while in yellow region, in this case, there is no non-monotonicity. And this figure basically says that I'm going up from here. Of course, if your noise is 0, I mean, here I fix my sigma, effective regularization, and I increase my effective noise, and of course, it always gets worse. This is trivial, but this is interesting. Okay, so what we find further, maybe as a side, that for kernels with larger width, so larger bandwidth, we find that regularization decreases, so they become more susceptible to double descent. Finally, I'm gonna show an application of this to neural networks. Of course, NTK is a dot product kernel as well, so you can do all the same things. What we find is that this is numeric evaluations, and then what we find that for different layers, we can plot what effective regularization is, and what we find for higher layers, effective regularization is bigger for first several modes, and then later this just changes. So deeper networks basically might imply that they are going to have less susceptible to double descent or overfitting. Here we show how, so the dots here are the kernel regression. The X's are neural network, actual finite with neural network experiments, and the solid lines are theory. This still fits perfectly well up to some point where when my number of samples reaches to the number of finite width in my neural network, and you start seeing some deviation from theory. This we can't explain. because as I said at the beginning, that this is I fix the future. So I can't really explain with this theory how model-wise double descent works. But yet it works up to some point. So if you are really in over-parameterized regime, this theory will still work. Here is another example, is that if I vary the width in my neural network, I see that this double descent peak for model-wise double descent peak occurs earlier. So that's basically what I have. And as conclusion, we identify three important things. One is spectral bias in kernel machines, where first modes learned first. Second of all, there's target kernel alignment, which basically says that if you place most of your power in the first modes, then you will learn faster, which makes sense. And there is no monotonicity in error in the presence of noise. In general, what we obtain is an analytical theory of generalization with good empirical agreement. And for a given label noise, we can actually find an optimal choice of regularization, and so can be applied to neural networks and real data sets. So thank you very much for listening.
Thank you so much for your very nice talk.